Namaskar my dear friends. As we have been seeing intelligent power module design, so in this session what we will understand is we'll understand the features of over temperature protection and as well as how we can design circuits for our over temperature protection, and we'll monitor the temperature of the IC when it is working inside a module. Okay. So let's get into the over temperature protection circuit that is offered by SLIMDIP series. We are actually discussing about the IPM coming from Mitsubishi Electric. Okay. So as you can see here, we have SLIMDIP series have over temperature protection function by monitoring LVIC temperature rise. Okay, so the LVIC is there, which is our low side gate driver. So this low side gate driver will be having a temperature change based on the overstress on the IC. So what happens is as the LVIC temperature exceeds, it keeps over temperature tip temperature. Okay, and this indicates by the fault output signal. So we'll see what happens actually. So as you can see here, my over temperature protection is given at trip level, which is up to 130 degrees centigrade typical value. So once the IC reaches to 130 degrees centigrade, my over temperature protection trips. Okay, and at that time it will shut down, so fault output will come, like a fault output will be indicated, and it will be low until it reaches to 120 degrees centigrade, and when it reaches to 120 degrees centigrade, again it will restart the system. Okay, so this is the main functionality of that over temperature protection. Now coming back to the timing diagram that it works. So how it works is, let us say we have the control input, which is actually my PWM signal, based on which my IC is working properly. So this is my PWM signal that is going to the uh, low side gate driver circuit or high side gate driver circuit everywhere. Okay. Now coming back to the protection circuit state. So protection circuit state, as you can see, we have this low and then it will be set on. I'll tell you when it is going to set. If you see temperature of LVIC, which is low side gate driver part, slowly the temperature is increasing, and as soon as it crosses the trip level, the set, protection circuit goes high. Now unless it reaches down, then only again it will reset, otherwise it will never reset. Coming back to output current on the IC, so output current was proper in each of the control input, and at that time when it has shut down, it has gone below, it has gone 0. So there is no output current that you will be seeing in the IGBT. Understood? So IGBT will be actually shut down because it has crossed the temperature of over temperature trip level, and as soon as that trip level was crossed, the error signal has gone 0 that time. So as you can see, error is indicated on the fault output pin by going low. Okay, so this is my low and this was high. If this is high, then there is no error. When it goes low, that means it is having error. So this is how the timing diagram works. We have control input, we have protection circuit state, and that is inside, and this is temperature rise that will be there on the IC, and this is our output current that is properly working, and when it crosses the trip level temperature, it goes low, that is IGBT is not working, and that time you will be having a fault output error signal. Okay, so let's get into the circuit design of this over temperature circuit. So what happens is, if you see uses of this particular function, so let's get into the characteristic directly, because we have already seen how this LVIC by built-in temperature sensor, it is measuring the temperature of the IC. Okay, so if we talk about VOT characteristic, that is voltage on the over temperature pin, so it has a capability of sourcing a current of 1.7 milliamperes. Okay, 1.7 milliampere will be the sourcing capability, and sink capability on this pin will be 0.1 milliamperes. So anyway, our aim is to get the output from this pin, so maximum we can get it 1.7 milliamps. Okay, so as you can see, this is the part inside the IC, complete part, this up to this part is inside the IC, and we have the output pin and ground pin. Okay, so this is the pin where we will be taking the over temperature voltage output as a analog signal, and this one directly can be fed to my microcontroller ADC pin. Okay, and let's say my microcontroller is working with a 5 volt logic, so it is good to go ahead because my VOT can reach up to 5 volt logic that we have already seen in our recommended operating temperature. But this is not a good method to connect directly. What we can do always is, if we have to connect with this, I mean if we have to connect in this manner, then what we can always do is, instead of directly connecting to this, we can have one resistor and one capacitor. So this is kind of my RC filter. Okay, so this RC filter can have a value of, let's say, 100 ohm, and this can be, let's say, 0.01 microfarad. Okay, that is 10 nanofarad you can keep, or even 1 nanofarad you can keep. Okay, so you have to make sure the time constant, that is my tau equal to RC, must be less than 2 microsecond. Okay, or less than 1.5 microsecond. That you have to make sure. That's the reason I'm giving you not zero point 0.1 microfarad, it is 10 nanofarad or 0.01 microfarad. Okay, so this was all about this particular circuit. Another circuit can be this form. Let us say we are detecting the temperature lower than room temperature. So basically, suppose the IC is having working in a low temperature. In that case, what happens is, this output voltage will not be very high. Okay, it will be very low voltage. Let's say our temperature is less than 25 degrees centigrade. At that time, my NTC is giving you very like high value. Because of that, the output will be very low. So at that moment, we have to have a pull down resistor of 5.1 kilo ohm, and then we to my microcontroller. Okay, so if you want, still you can have one RC filter and then send it to the microcontroller, and make sure microcontroller is working with let us say 5 volt output, 5 volt control logic, and send it to my ADC pin. Okay, we can always send this particular pin to a separate ADC converter, and then from there it can be sent to MCU pin, but that will be increasing the cost of this particular design. Hence we generally send it to inbuilt microcontroller ADC. Okay, good. If we have a position of, let's say, my microcontroller control signal is lower than 5 volt, let's say 3.3 volt logic or something like that, 3.3 volt logic or 2.5 volt logic. So these days microcontrollers are coming with low level, like lower voltage logic levels. So in that case, what we will do? So in those cases, what we can do is, let us say using with low voltage control microcontrollers. So in that case, we just have to do one thing, is we can put one clamp diode. Okay, so this diode, let us say it has been fed to how much? Let's say 3.3 volt, and this is also 3.3 volt that is there. So what will happen is, this 5 volt, if it is coming, or more than 3.3 it is coming, then it will be synced. Okay, so this is how it is going to save my microcontroller ADC input. So my microcontroller ADC input will not be stressed with more than 3.3 volt. Okay, and at the same time you have to make sure two things. Keep one RC circuit here and send it to this. It is always a good method to send this particular VOT pin to the ADC pin by putting a buffer as well. So since it is having inside buffer, you can see here internal there is a temperature signal, and it is going to get amplified through this particular particular amplifier, and then it is being sent out to the VOT pin. So we are not putting the amplifier, buffer separately, but it is always a good method. Let us say this is the point where VOT is there, so that pin always can be connected to one buffer. So let us say we are going to have here buffer, and this can be grounded. So this will be my connection at this particular position. Okay, so this is how, and it can be sent to my ADC of microcontroller. So this will increase the cost again. However, this is a recommended method, so that you can have a proper amount of current as well to the ADC. Let's see another protection level. So what happens is, let us say we are working with low level voltage controller, let's say 3.3 volt or something like that. So in that case, instead of using the clamping diode, we can have a voltage divider circuit also. So R1, R2 we can utilize. So let us say we are going to use R1 as, let's say, 1.74 kilo ohm, and this can be, let's say, 2.49 kilo ohm. Okay, so in that case we can have like let's say my VOT is going up to 5 volt maximum. So in that case we will be limiting our like DVO2 at how much it is. Let me just calculate and show it to you. So it can be 2.49 kilo ohms. In that case it can come up as 2.94. Okay, so this will be limited to 2.94 volt. Understood? So this is how we are going to limit the output voltage by having a voltage divider, and then send it to the if you want you can send it to one RC filter, and then you send it to one buffer, and then you send it to one ADC of the microcontroller. Or otherwise for low cost application or something like that, we can directly send it to my microcontroller. Good. So hope you have a very good understanding now. So why are we doing these different things? Like basically at low temperature we have to have a pull down resistor. At high temperature we don't need to have pull down resistor. We can directly connect it to the microcontroller ADC. So if you see the voltage output, like on the over temperature pin versus the temperature variation. So this is the graph that is given from the data sheet, and as you can see, as my LVIC temperature is increasing, that is my low side gate driver temperature is increasing from, let us say, minus 25 degree centigrade to 130 degree centigrade, right? And as you can see, like three values are there. One is maximum, then typical, and then minimum. Okay, so we'll talk about typical values. So below, like around 25 degree centigrade, we have very low voltage. So you can see it has very low voltage. So in that case we need one pull down resistor. So that's the reason 5.1 kilo ohm was used. Okay, so in that case, and this can be sent to my ADC. And for temperature bigger than or higher than 25 degree centigrade, this is normal range that you can see from 25 degree centigrade to up to, let us say, 100 degree centigrade. It can give you a very good voltage, good amount of voltage output. Okay, and for more than 100 degree centigrade or more than, like 90 degree centigrade, you are going to have higher value than 3.3 volts. So in that case, if we are, our microcontroller is working less than, like 5 volt, that is, let us say, 3.3 volt logic. In that case we need a resistor divider or something like that, like this, like let's say R1 R2, and this is how we can divide our output voltage to lower than 3.3 volt, and then send it to my microcontroller ADC. That's the main understanding we should have. Otherwise, one more option was put one diode and then send it to my ADC. So this is my VOT, and this is my, let's say, 3.3 volt. So this is how it will be like forward biased, and this is how it will be saved. So this is how we are actually working with like low voltage microcontroller, and as well as completing all the circuits. So same way almost all the like manufacturers have given the circuit. Let us say we talk about like ROM semiconductor. So ROM semiconductor also has given almost same circuit. The VOT pin can go through RC circuit and then send it to my microcontroller ADC pin. Okay, it is a good practice that you can put, let's say, point X to a buffer, and this buffer can go to my ADC. Like that it can work out. So basically buffer will be working like this. This is my ground, this is my buffer, and then send it to this. So this point will be input, this point will be output to my ADC. If another circuit, if you see, like we have the temperature lower than 25 degree centigrade, as I told you, so you put a pull down resistor 5.1 K and then send it to my microcontroller ADC. So this is another method. Coming back to like VOT with low voltage controller, let's say we have a 3.3 volt controller. That time we can put one clamping diode with, let's say, 3.3 volt, this one, and in that case what will happen is whenever the voltage is more than 3.3, it will be like sorted here, like it will be kind of syncing, and this is how my IC will be saved, like my ADC pin will be protected. Okay, coming back to another point, what I told you is, let us say we can have a voltage division capability. So voltage division is actually recommended instead of just putting the diode. So in this way you can see my DV divided voltage output over temperature will be how much, VOT, that is, you can see it is very easy, like this is my, let's say, V1, this is my Vx. So my Vx value will be V1 into R2 by R1 plus R2. Okay. So Vx will be equal to V1, that is VOT, multiplied by R2 divided by R1 plus R2. So in that case we can utilize. However, one more recommendation that is given is so that the current is not reduced very like much. So in that case we can keep R1 plus R2 approximately 5 kilo ohm or something like that. So that's the reason I have given you two set of values. One is 1.74 and 2.49, and another one is 1.78 and 2.67 kilo ohm. So these are standard values of resistors that we have utilized. So hope you have a very good understanding about how to connect the VOT pin protection label to the microcontroller ADCs or any other place where we want to have a like this particular analog voltage to be given. So if you do have any questions regarding any kind of design regarding the uh, voltage over like protection or over temperature protection circuit for your IPM design, you can always put down your queries in the comment box and we shall be giving you the right answers as soon as possible. Thank you so much.